Yes. For minimization of the assignment or the example that we had last week. I didn't get what is the threshold for minimization. That was a dumping parameter, for instance.
No. What I saw how most of the class were doing. You did stop procedure when the table ends, but one should go forward either until 10 or until the convergence is achieved. And convergence, you can set up it yourself.
So this parameter should be minimized, right? What did you mean?
This one.
Or different. Delta U should be minimized?
Delta U should approach as close to 0 as possible.
So it shouldn't approach to 0. It should approach to a number. Maybe be negative, maybe.
Yeah, absolute value should approach 0. But you can say that threshold is, say, like 0.3 or 0.1 or 0.5. It's your choices for the human. Some of you were complaining that this doesn't work out for feedback. But they made very
keep it in the direction.
What?
You should keep it in the direction toward the monitor.
Yes. And under the table, when there was the next presentation, I may not react, but under the table there is a supply tables. Are you ready?
Yeah.
Okay, let's start right now. So we do have last 5 minutes of the previous lecture. So the presenter number.
You didn't present that.
Yeah.
Yes. Okay.
Yeah. Rebecca Todman, and she will finalize our knowledge about using Gauss-Hilbert geometry optimization.
Yeah, so welcome to my presentation about cleaning and optimizing geometry in Gauss-Hilbert, which will basically teach us how we get from this messed up molecular structure to a better one, to an optimized one. And I assume that we all know how to build a molecule. So I was
computer.
Oh, yeah.
okay, that's it. Okay, so we start off with this completely messed up molecular structure of propanol. You say that? Propanol? And what we do to optimize it, we go to this calculate button and select Gaussian calculation setup. The shortcut for that is Ctrl-G for those who care. And that will open this menu. And we change the job type to optimization because we want to optimize the geometry. And we specify the method to ground state and mechanics, and UFF, that means the universal force field. Just like put that and then submit it. So when the job ran, we will see this, and it gives us 2 results files. The checkpoint file, which is like, I know you play video games, like the checkpoint is like the last step, like when you hit the checkpoint and then go further and then die, you will go back to the checkpoint. This is what the checkpoint file is. But we want the .log file. This is like our output file, like the optimized tree. And if you I click on the log file and then say, okay, you will get the optimized geometry in Gauss view, but the alternative would be we go we start from the beginning. We have our messed up geometry, and another way to optimize it is to go to File and save it as an input file, and then go to MOVA Xterm and submit it in MOVA Xterm. And when you go to the directory where you save your file and you open this input file that you got from Gauss view with the vi command, you will see the input file, and very important to check is this line where we specify what we want Gaussian to do. So we say up for optimize, and then UFF for universal force field. And geometry is just the connectivity, how the atoms are connected to each other, and then we get the x, y, z coordinates, and this is the bundling and some more information. And very important for Gaussian is that you have empty lines at the bottom of the input file because it won't run. I don't know why, but it's just very important to have those empty lines. And then you exit the file, submit the job with G09 for Gaussian 09, the program we use. And then you have your input file, and what this means, you write it into the output file. You can name it whatever you want. Very important is that you have name it .log, because this is what Gauss view can read. And then when you go back to Gauss view, you can find your output file, and it's important to change the file type to .out or .log, because it won't appear otherwise. And last but not least, we have our messed up geometry, and we can just hit the broomstick to clean it up, and whatever of the three methods you want to do, you end up with the optimized geometry. And that's our goal, and that's the end of my presentation, and feel free to ask questions.
Okay, thank you. Any questions? Any suspicion that something can be better, or regimes of this?
Which one is better? Which technique is better? It's hard to say.
I mean, the broomstick is very easy. If you have small molecules that are easy to optimize, you might want to use the broomstick. I don't know, I submit them
But
like this.
doesn't work all the actually.
So in which specific case broomstick is poor choice, the worst case one?
Yeah, but it's the easiest.
It's the easiest, but in which case broomstick can be applied in many cases as a first step, but in which case it is not reasonable?
When you have separate carbon, it's hard.
If you have more complex molecules,
I don't know what's the best answer. I would answer if the bond order is not known. If you draw something but you do not know whether it will be bond between a group of atoms or maybe double bond or conjugated when it needs to select. So in this case, broomstick may give some sort of.
yeah.
More questions to Rebecca?
Also, they use the same algorithm on the geometry.
And broomstick? No. The broomstick is just using some standard bond lengths and angles from database. More questions? If no, let's thank Rebecca once again. And now we finally conclude the chapter 1 and go to the chapter. So if you are bored to listen to me, you may read handouts that are in front of you. And there is a joke or like example that is probably useful, but I'm not quite understanding. You may read it and discuss between yourself. Like, they're telling about having a bucket with 2 cold apples and 2 hot potatoes, and then closing eyes and trying to pull one, and before pulling, calculating the probability. So you may read and discuss between yourself, and this will be the subject of today's meeting. Although we will not, the subject is neither potatoes nor apples, but the logic is similar. So who we are and what are we doing? It is computational chemistry. Of course, we are trying to predict properties of molecules and materials, and we agree that all materials and molecules have electrons, except the proton. Electrons do have wavy nature with the base Schrödinger equation. We started from molecular Schrödinger equation that takes into account both nuclear and electronic degrees of freedom and quantum. Then we separated electronic and nuclear degrees of freedom, accepted Born-Oppenheimer approximation and monogalactic non-organic couplings for low temperatures, and agreed through Ernst theorem agreed that expectation values of position atoms can be either optimized or propagated over the time by molecular dynamics using Newton equations, or equations that look like Newton equations. We will forget about ions for about a month. Now let's focus on electronic degrees of freedom only. So there will be slides, but I think if we discuss it informally, it will be more helpful and useful. So we select certain terms in the Hamiltonian and pull them out of overall molecular equation and set up time independent Schrödinger equation, which gives us wave function of all electrons. For next month and a half, we assume that nuclei, ions are nailed down to the, whatever they are. And the reason of nucleus is only the source of attractive electric field that brings atoms together. And our goal is to find wave functions of all electrons and energies, energy. Lower ground state energy and maybe it's, well, excited states and energy are also interesting, but we'll start with just ground state energy of all electrons. What is our plan, or what are the challenges in this project, in this path? So the challenge is basically the same at all steps of our course. A large number of degrees of freedom. So if you have many electrons, each of them has 3 Cartesian projection. And if you have many electrons, it will be a wave function that depends on so many independent variables. Even we kicked out nuclear degree of freedom, it's still deadly complicated. So we need to reduce the number of degrees of freedom. So it's major problem. There are additional ideas and features that we'll go over. So do you know any of the realistic quantum problem when one can find wave function, electronic wave function for sure, absolutely correct, with very high precision. For which natural system, for which quantum problem everyone in class knows the solutions. Sample, if there is a problem.
Only three systems.
Which one?
Hydrogen.
Yes, absolutely correct. Hydrogen atom, right? So if there is one electron moving around a single proton, one can find solutions, wave function, S, P, D, right? In the past, I mean, in the past, not like in the time of ancient civilizations, but in the past related to this course, we were discussing an idea of dividing and conquering, of splitting separation of variables, representing wave function of many independent variables as a product of wave functions of lesser amount of variables. So the idea that we will cover start, that we will deal with it for a month, is that wave function that depends on positions of so many electrons as many electrons in the system would be really great to represent as a product of wave functions that depend only on one position of one electron. On wave functions of atomic wave functions that look like hydrogen atomic wave functions. And I'm just skimming through, we will go into details. So we focus on electronic wave functions, we want to simplify it, and our general direction of thinking is to chop, to factorize many electron wave functions as a possible product of one electron wave functions. Free cheese is only in mousetrap. Probably this is not always possible, so there will be some price for doing this. And the price for doing this originates from a very simple fact that electrons interact with each other. They repel, right? And the repulsion of electrons is summarized in another concept that those of us who are taking freshman chemistry or high school chemistry know as Pauli exclusion principle. Does it click something? Right? So there are in a certain atom or molecule, there are no identical electrons. All electrons will sit on different orbitals, right? And the reason for this principle is electronic propulsion, and there is a mathematical concept summarizing, representing this principle. So the mathematical concept that reflects Pauli exclusion principle is known as a Slater determinant, and it is a subject of today's paper. So, did you have linear algebra? You are not surprised with the concept of determinant. Okay, then I will introduce Slater. You already know determinant, then we just put them on the same page. So by the end of today's meeting, we need to confidently speak about Slater determinant and being able to write it down. Start, set, roll. So, if you are interested who is Slater, there is a wiki page, Wikipedia page, and the connection I have to John Slater that when I was a postdoc at the University of Florida, across the postdoc office where I was sitting, there was an aquarelle painting made by John Slater, because he spent some years at the University of Florida. Well, we know about his scientific achievements, but he also at least painted one aquarelle. And here is a brief summary of our previous lectures. So we consider nuclei and electrons, set up trivial equations, split nuclear degree of freedom and electronic degree of freedom. And from now on, we are focusing only on this equation. So we find phi sub k and e sub k. And R positions for nuclei are fixed. So for month and a half, we do not care about that. This is your homework about position. This is an algorithm, optimization algorithm that you practiced in the other homework, right? Repeat. Apply some equivalence. And okay. When we were discussing an idea to apply Ehrenfest theorem and use Newton equation for nucleus, we justified or we motivated this step by the fact that one needs too much information. If one represents each degree of freedom as a set of grid points and represented numerically, then amount of grid points to represent nuclear wave function will be like terrible. The same thing is for electrons. If we consider there are 3 Cartesian coordinates for each electron, and each Cartesian projection will be split on, let's say, 10 grid points, then one can just get scared by assessing the amount of data points needed to store the full wave function. So if you have wave function that depends on several electrons, each freedom, each electron has 3 degrees of freedom, then and if 1 degree of freedom includes only 10 grid points, then hydrogen atom will need just 1,000 numbers. If I do not know how to solve Schrödinger equation, but I know how to run codes and represent solutions in numerical. If you have hydrogen molecule with 2 electrons and 3 degrees of freedom per atom, then it will be a million grid points. If you have single carbon atoms with 6 electrons, so it will be this much data points. And I think 10 to the 12 is approximate capacity of the regular cube terabyte. So it's only Newton time Newton terabytes for 1 carbon atom. You all should do full wave function. And if it will be a small molecule of acetylene, and do it just blindly, solving, formulating Hamiltonian, formulating wave function as grid points, and solving it numerically, it will be this much data points. So we will fail even to compute acetylene with fixed movement. So it's definitely not a right direction of thinking. We need to design approximations and simplify the problem, even if we lose some precision. We better lose a couple of % of precision rather than treating so many data points. It's completely legit. So the reasonable, logical idea is to attempt separation of variables. What if one can represent this long wave function as just a product of many electron wave function as one electron wave function R1, and another wave function of R2, another wave function of R3, and then assume that it will be reasonable representation. The first person who did it was Hartley, and we will discuss it in a week or two why it does not put in details. But basically, if we represent many electron wave functions as a product of one electron wave functions, it will mean there are 2 questions. First, what will be the functional form of one electron wave function? And the answer is simple. We logical if you know, not logical, it's tempting. If you know solution for hydrogen atom, let's use solutions for one electron hydrogenic wave functions as building blocks. But there is a second question. If we represent multi-electron wave function as a product, it means that shape of wave function for first electron and shape of wave function of second electron do not depend on each other. It means the variables, position of first electron and second electron, are completely independent. Electrons are independent. But intuitively, we can feel that it is not quite right. Electrons are repelling each other, and their shapes of one electronic code and another, if there is more than one electron, are not independent. And this is the major challenge of computation chemistry. If one would design a universe where electrons do not repel each other, this course would not be needed. We will do separation of variables, find solutions as just product of atomic functions, and that. But fortunately or unfortunately, they repel. If we discuss details of their repulsion, if we discuss the mathematical optimal way to represent the repulsion through solid experiment principle and Slater determinant, it will pave a way for efficient addressing, for paving a way how to formulate the electronic wave function in a way that minimizes numerical effort. Not that everything will be super simple, but it will be at least possible. It will be not like 10 to the power 42 for a second. It will be much less. So I'm putting this face here because when I was teaching this course for the first time, I needed to go to a conference during this lecture, and the postdoc from my group was preparing slides for me, so Mikhail was helping and keeping credit to him 3 years. So if we have all the electronic degrees of freedom, there is a kinetic energy interaction between electron and nuclei and electron-electron repulsion. In case we have only one electron and one nuclei, hydrogen atom, then solutions are known, and if you all are acquainted with solutions. In the modern civilization, kids in kindergarten, or at least in school, are looking at SPD orbitals. But if we decide to solve the hydrogen atom wave function from scratch, it will take like half of a semester. It's very pleasant for mathematically oriented, but unpleasant for those who do not care about math problem. So the solutions are formulated in terms of radial and angular parts, and they both are spherical functions. So they're not like sines, cosines, and exponentials. They are special functions. But it's just their name. But they're only not spherical permanent. And if we are using them just as humble users, what should we look at in these equations? If you're driving a car or shopping for a car, we do not need to know all details how it is arranged, but we need to look on specs. So the specs of the hydrogen wave function, this term is dropped because we do not have other electrons. No propulsion. The quantum numbers. There is a principal, orbital, and magnetic. please give me a little sign if these three words are not known or you are shocked by the list. Principal, orbital, and model. Everyone is happy with them?
So you use one electrons to represent a bunch of electrons.
Yes, we use one electronic solution to represent multi-electron wave function, and for like 3-5 minutes we focus on the one form of atomic wave functions, one electron wave functions. Wave functions for hydrogen atom. There are many solutions, right? With different energies and different angular momentum, and the solutions for hydrogen atom are specified by 3 quantum numbers. Principal, which determines energy; orbital, that determines maximum possible level of angular momentum; and magnetic, which determines projection of angular momentum on the axis. Yes? Right? It's not a big surprise. You've heard it before. Okay. And these numbers are here, and this is just a list how they appear in solution. And a little note that we may not need, but who knows, maybe someone will benefit from it in a couple of years in the career. Oh, okay. The angular part of the hydrogen wave function contains imaginary part, imaginary exponential, which means it accumulates phase as we go along the azimuthal angle. But in a minute we will look at the traditional SPD orbitals, which do not have imaginary part, right? We just draw them like balloons, bubbles. So there is a standard trick that solutions with same absolute value but opposite sign of the magnetic quantum number, with this exponential part, this plus and minus sign, are added together. And then by Euler's equation, these two exponentials convert into cosine. And this summation of the solutions of atomic wave function is typically analyzed and drawn when we speak about SPD orbitals. They are real. So it is a superposition of angular momentum when having opposite values. See projection. Yeah. You recognize these figures, right? So those are atomic wave functions. The decision to use 3 quantum numbers is just mathematically, it originates from the way how they are found. And the principal quantum number determines the energy, and orbital and magnetic quantum number determines the dependence of wave function on the azimuthal and theta angle. So the s orbital that we all are happy with is orbital that is isotropic, doesn't depend on angle, and p orbitals do have one nodal plane. And this green and red colors symbolize positive and negative. the trick on the previous slide about getting together and speaking about superposition of solutions with opposite values of magnetic quantum number is justified because in simple cases of hydrogen atom, energy does not depend on magnetic quantum number. So if we scan values of magnetic quantum number minus 1, 0, 1, all these p orbitals will have the same energy, right? And if we reshuffle them by adding and subtracting, energies will not change. So as we go higher in energy, more and more values of angular momentum become allowed. Right? The lowest energy you have only S, or next you have S and P, so angular momentum 1 is allowed, and when you go higher, transition metals, D electrons also become allowed. And for maximal enabled value of angular momentum orbital quantum number, there is a degeneracy. There are possible states with the same energy, same total value of angular momentum, but different projections of angular momentum on z-axis. And so this magnetic number changes from minus this number to plus this number. Minus 2, minus 1, 0, 1. And for set of these three quantum numbers, one can draw atomic wave functions, right? Which later we will use as a building block to form multielectron wave function. Good. Dependence on energy and principal quantum number. So here we show dependence only on angles, and in three-dimensional space we can replace three Cartesian projection on spherical coordinates: distance from origin, one angle, and another. So now we are looking on principal quantum number and depending on the distance. So for the S orbital, there is a probability is maximum near the center, and then it decreases. So we are looking if we are going from the center of this wave function and depart away and look at density, where electron is most probable. If you look for the second orbital, it will be again maximum in the center, then a dip to 0, and then it growing again. If you look for p orbital, there will be 0 probability at near the nuclei, and then it increases and then decreases. And for this figure, you can see it here. Near the center, it is 0. And I'm going to temporarily exit from this presentation and go to the website. So you're aware of periodic table, right? List of elements. And there is a really great site, table.com. So here there is a tab orbitals, then you select on the atom, and then it allows to browse over the quantum numbers and all possible orbitals. So I know that we all must be aware of solution for hydrogen atom and write equations if we select academic or industrial research or teaching career. But when we are short in time and we need just qualitative assessment of what these orbitals are, this website is a good tool. Because equations are good, but they're a little bulky. And if you need just to interpret, so when can we use it? So if we keep angular magnetic quantum number 0 and change only the principal, it will show that it maximum tip, then another maximum then goes to 0. If you go further, it's more dips and maximum. So the S orbitals have 0 angular and 0 magnetic quantum number, but they have the fringes pattern as we go from the center to outside. Okay? So it's like shell, several things inside each other. If we go into the major quantum number, principal quantum number 2, and we first allowed value for orbital quantum number, you will see this shapes, this one model plane. You see they have different value of projection or magnetic projection. Right? If you go to the principal quantum number 3, so there are 3 p orbitals with orbital quantum number equal 1, and they have, in addition, they have fringes as we go from center to outside. That corresponds to larger energy. And if you go further to a larger value of orbital quantum number 2, you will see shapes that look like a flower with 4 petals, right? Except the one in the center with magnetic projection. You go 0, then it looks like you know, a donut with 2 holes together. If one looks for higher values of angular momentum, there are more exotic shapes, and with time you can use them, especially if you plan to do a project on radioactive materials like actinides or photoluminescent lanthanides. Okay. So, why did we review these wave functions? Because they are building blocks. So we are approaching to the main task of today's meeting, to start discussion of the electron-electron repulsion. So if you look on the this piece of paper that is distributed, if there is no enough, maybe it's on the second row. And if you look through, you will see this this text. It goes after the joke about potatoes and peppers. So, since consider a system like helium atom or H2 molecule with 2 electrons, consider that we are trying to represent wave function as a product of single electron wave functions, and consider whether it is legitimate or not. So through this informal discussion, there is an idea that they are not independent. The shape of one electron that sits on one orbital, shape of orbital where first electron is sitting, depends on shape of orbital where second electron is sitting. And this principle is reflected in several ways. If you go back to the thing, there is a Bow principle that if you have an atom heavier than hydrogen, you put more electrons. You cannot put all electrons into the S state. You put 2 electrons in S state with opposite spin, and then you fill next cell with 2 electrons, next cell. So you are filling it like seats in the movie theater. More and more, the whole number of electrons fill lowest seat and then go upper and upper. So this originates from interaction between electrons, from their mutually affect each other, and if we decline any mass, then it can be formulated as Pauli exclusion principle. There's no electron, there are not 2 electrons that share the same set of quantum numbers. So as soon as we contribute more electrons to the atomic or molecular system, by mandatory, it will take a state with different set of quantum numbers. Good. Now, is it possible to maintain this requirement by a simple product of one electron wave function? Or we need some to design more advanced construction of the multi-electron wave function from single electron wave functions to maintain this Pauli exclusion principle? It is a little intellectually heavy step, although I'm trying to simplify it, but I was hating it in my undergraduate and I keep hating it. Do you see this writing? Okay. So, right now, we are at the stage of designing our theories. We can hypothesize anything we like, then later we need to justify it. Let's hypothesize that we can set up a superposition of the products of one electron wave functions with slightly different things. So we will do a product of first and second orbital. Under 1 and 2 here we assume like set numbers. Orbital 1, orbital 2, orbital 1, orbital 2. But we will swap electrons. Like in the first term, the electron number 1 sits in the orbital number 1. And it is a little crazy thinking because we assign numbers to it for the orbital. And electron number 2 sits at the orbital number 2. In the second term, electron number 2 sits at the orbital number 1, and electron number 1 sits at electron number 2. So both of these terms are product of one electron wave function. But, huh?
Is it part of this?
Oh, yes, for multi-electron wave function. If we swap the order of the electrons, if we swap the order of electrons, like now electron number 2 will be in place of number 1, number 1 will be on the place of number 2, one will see that 3 terms with positive and negative sign will swap, which will mean that overall sign of the wave function will be changed from positive to negative. So if we replace 2 electrons, sign of wave function change to the opposite. And this property is referred to as the word antisymmetric. So symmetric with anti. And here is the most beautiful, not in calligraphy, beautiful in idea thing. Suppose I want to violate our exclusion principle. but I already accept this antisymmetric wave function. So I accept antisymmetric wave function on one hand, and on another hand, I want to violate power exclusion principle. What will happen? So I will try to put both first and second electron into the first orbit. In terms of hydrogen atom, it means that I will try to put two spin-up electrons in the lowest s orbit. So orbital 1, orbital 1, electron 1, electron 2, minus orbital 1, orbital 1, electron 2, electron 1. That you give 0. So instead of wave function, I will get nothing. And this illustrates that antisymmetric construction of wave function prevents single person from violating power principle. Okay? So if we always accept antisymmetric shape of wave function, then it is not possible to violate power principle. So swapping the order of electrons changes the sign, but the probability distribution for the swapped electrons will be the same, because probability is absolute value squared. I was trying to violate power principle once again, and I failed. Okay. So we are setting up a goal to solve electronic Schrödinger equation for electronic part. We need to find this phi sub k that depends on multi-electron wave function. And we need to respect our exclusion principle. Due to this necessity, we agree to accept antisymmetric shape of the wave function. And once again, the goal of all of this activity is to simplify numerical problem and amount of information we store. So we want to replace this wave function by a product to separate variables. But we can separate variables only with an account of power exclusion principle. Instead of product of atomic wave functions, we need to use this antisymmetric shape. Function 1, function 2, or function f, function g, function g, function f. First, second, with minus. Does anyone object this plan or have some discomfort? You sign if anyone objects. No. That's so that you do not ask questions later. Please raise hands who is against antisymmetric wave function. Please raise hands if you support antisymmetric wave function. Okay, it is recorded. Thank you. And now let's recall your maybe first meeting in linear algebra, the definition of determinant. So if you do have 2x2 matrix and practice concept of determinant, it will be diagonal minus off diagonal, right? Let's look. Let's identify analogy between the concept of determinant and our democratically accepted concept of antisymmetric wave function. In the antisymmetric wave function that you all voted for without any pressure, we have like product of 2 minus another product of 2. And in the concept of determinant, you also get product of 2 minus product of another. Would it be possible to construct such a matrix by taking the determinant of which we will get antisymmetric wave function? So if we formulate a matrix where index of wave function will be a row, and index of the electron will specify a column. So first row, wave function 1. Second row, wave function 2. The first electron, column 1, the 1 column. Second electron, column 2, R2. And now let's practice the principle of determinant. Row by column. Diagonal. Phi 1 R1 minus phi 2 times phi 2 R2 minus phi 1 R2 times phi 2 R1. Good. So it is exactly the same as antisymmetric wave function that everyone in class coded. Why do we need a determinant? You know, it's just a good word to label a concept on one. On another hand, if you wouldn't have any computers and you would do all the calculations by pen and paper, which I hope you never should, writing a long list of products with antisymmetry will become very unpleasant for like more than 3 hours. But if you take this compact form, it will be less writing, and still it represents the same concept. So if we talk between each other and we tell like, let's consider multielectron wave function of 4 electrons. To highlight that it is antisymmetric, we will write it down as later determinant, and then we will write determinant. So when we do have 2 electrons in 2 wave functions, it will be the same number of symbols. 1, 2, 3, 4, 1, 2, 3, 4. But as soon as we get to a bigger number, writing down the later determinant will be saving space on your piece of paper. And if each of the atomic wave function is normalized, then multielectron wave function will be normalized as well. But we will cover it. Later. Anyone wants to object the Slater determinant? Anyone wants to support the idea that Slater determinant is wrong? Please raise hands. No. Anyone who believes that Slater determinant concept is correct, please raise hands. Okay, accept. So from now on, we will base our next considerations on this concept of Slater determinant. And here's just a little illustration. If you like MATLAB or if you like visualization, so it will be a little easier intellectually, but in the next 2 slides there will be no new concepts. Suppose we do have particle in the box. Suppose we all remember how solution for particle in the box look. So the solutions will be sine functions, sine x, sine 2x, sine 3x, and the size of the box in the denominator. if the size of the box is pi, then we do not have pi and size of the box in the argument. So it will be just sine x, sine 2x, and sine 3x. Next, let's assume that we want to squeeze more than one electron in this one-dimensional particle in the box. And we want to immediately, based on your democratic votes, we need to accept antisymmetric wave function. How can we visualize it for humans, for us? It is one-dimensional particle in the box, but first electron and second electron may have different coordinates, right? Therefore, we are using two-dimensional representation. So it's the same coordinate, one-dimensional box, but x1 will be position of the first electron, x2 will be position of the second electron. And the colors here, orange will be positive, blue negative, green neutral, 0. So, first term in the antisymmetric wave function. Let's go x1, it should be 1, and x2 should be 2. So, as a function, we are building a product of two sine functions. Along x1 direction, it will be just one hump, right? Half period of a sine. For second coordinate, it will be a sine going up and down, right? And now we are building a product of this function is maximum in the center and going to 0 at the edges, and here maximum in the first half, minimum in the second half, and going to 0 at the beginning, center, and the end. So it will be this. If I would do it three-dimensional, it would be too much information. So here it goes out of plane, here it is like going to a dip, and it forms this shape. If we form the same product, but we swap the order, so for x1 it will be 2, and for x2 it will be 1. So you have up and down orbital, and here we will go one up, and we make a product. So in the first half will be positive, second half will be negative, and will be zeros everywhere at the edges. So those are products, individual products of one electronic wave functions. But in order to respect Pauli exclusion principle, we need to subtract them. And if we just subtract these two things, instead of nodal plane going orthogonal to axis, nodal plane will go at the main diagonal. So this one is visual representation of antisymmetric wave function. And if we want to check the swap, the antisymmetry, if you swap the indices, the independent variables 1 and 2, it will be antisymmetric. Where it was a maximum, it will become minimum. Where it was a minimum, it will become maximum. If we would try to violate Pauli exclusion principle, if we will put the both first and second electron in the state 1, if you put 1 here and there, it will go flat green color corresponding to 0. So the take-home message that later on in the next meetings we will look for multi-electron wave functions in the antisymmetric combination of atomic wave functions.
Excuse me, we have
Meeting is done.
TA class.
Please.
And
Yes, I will collect.
thank you very much.
So meeting is done. everyone is welcome to depart, and I'll stay here to answer questions if needed.
Thank you. Have a good day.
Just one question. So for this line, they will have the same energy.
Yes.
Thank you.
I missed the first half of the lecture.
Yeah, I'll
We didn't do the part. Method.
yes. X1 changes from 0 to pi. Pi. But pi is 3.14.
Okay.
X1 ranges. X1 equals 0 some step. So it uses certain amount of grid points from between 0 and pi.
Thank you.